So looking at this paper, here's the answers. I wanted to make sure that we do this every single year. We normally have this on the quiz and on the test, but because we have no test, it's not going to be on there. Because our quiz is online, you're not going to be able to do this. On the semester exam, you better make sure you have your ruler, your protractor, and your colored pens or pencils with you, because it will be on the semester exam. All right? So this will be, we'll see later on. You had to count the number of waves, count how many crests, how many troughs. The waves don't always start at the middle. Sometimes it might be at the bottom or top. It just depends. What you do need to do for finding velocity is you kind of have to do two steps. Because they don't give me the period or the frequency, I have to solve for frequency first. So the number of waves divided by the time equals my hertz or frequency. I use that number to multiply by the lambda. And on this worksheet, it just says velocity. It doesn't tell you centimeters or meters. I don't know on the semester exam because I haven't finalized it yet. I don't know if it's going to tell you, give me the velocity in centimeters. I don't know if it's going to tell you, give me the velocity in meters, or if it doesn't tell you anything. So I just gave you both answers just in case. So kind of double check your answers if you have your paper. Here's the answers to the second page. And I just wanted to make sure that you got, oh man, I didn't do that one. How did I miss that one? What's that? Okay. That's all right. Now I am going to post the answers to the Thursday students at 11 o'clock, and I am going to post the answers for the Tuesday at 11 o'clock. Let me finish that, and I'm going to take pictures of them and post them on Blackboard too. So if you don't have this in front of you, that's okay, because you can go to Blackboard later on at home, and you can look at your answers and see if you got it right or wrong. And then the last page over here, those were 16 waves. This was only 2 waves, and that was 6 waves. I'm going to look at the color to make sure you colored it correctly. And I'm going to take a glance at your velocity. It does not matter if you use centimeters or meters. I just wanted you to take a glance to make sure you got your answers right. I will post a picture, but let me go back and do that one question I forgot. I apologize on that. So here are the answers. Double check. You're going to see it again, semester exam. On your notes, let's look at your notes. Homework is going to be last. Yeah. There you go. So on your notes, looks like this. There are a few things to go through today. I just don't think we're going to have enough time to finish them all. So what we have been doing is that last page, I haven't been able to finish it, so I had to video it on my phone because I don't know how to get the video. I have the video on a hard drive. I just don't have it. I don't know how to post it. I've been videoing it. So there's might be 2 things at the end that I'm going to have to video for you and show you, but I think I want to video it anyways and post it on there because there are some students who are out because of testing. We have STAR testing this week for some school districts and STAR testing next week for some school districts, just in case, tossing it out there. Let's take a look real quick. The important parts. The definition of simple harmonic motion is a motion that occurs over and over and over again. But let me give you an example. If I had a kid and there was somebody in a swing and they asked me to push them, and I pushed them one time really hard, and when I moved out of the way, they're going to go back and forth by themselves. Eventually, they're going to come to a stop or a rest, which is called dampening. Why are they coming to a rest? Because of gravity and friction. So when they get back to that equilibrium position due to dampening, okay, that is called simple harmonic motion. But what if that person is there on the swing and I push them and then they come back, and I push them again and then they come back, and I push them, if I continue to push them and to give them energy, that is not simple harmonic motion, is what I'm trying to say. The bird flapping his wings is not simple harmonic motion because he's forcing his muscles to move his wings back and forth. Remember, it has to do it on its own, and it's going to eventually come to a rest due to dampening. This is one equation which I think was super easy, and so we really haven't looked at it. It really wasn't even on the homework much. Elastic force, instead of F equals ma, it's K times D. So that's the equation we're using. Waves. So all waves have one job, which is carry energy. Why does it happen? It carries energy. Now, the cool thing about waves is that it's not actually matter, it's energy. And so 2, 3, 4 waves can actually occupy the same space at the same time. Now, waves are broken into 2 groups, mechanical or electromagnetic. Now, mechanical waves, though, they're special or different because they have to have a medium to travel. Electromagnetic does not have to have a medium. Could it travel through a medium? Yeah, it could, but it doesn't have to have a medium. Now, mechanical waves are broken into the way that they look, transverse or longitudinal. I went back to your notes and it's not on here. So on the quiz, semester exam or whatever, I don't want you to freak out. If you see the word compression or compressional wave, that's the same thing as a longitudinal wave. Okay? It's not mentioned in your notes, so I wanted to verbally tell you. A longitudinal wave is also called a compression wave or a compressional wave. Now, you are going to see test / quiz, whatever, when they say that a wave travels perpendicular to the energy. If this is the energy right here, moving from left to right, my ocean water is moving up and down, up and down. And look at this, it forms a 90-degree right angle, which means perpendicular to the energy. If this is my energy, energy, and this little spring hits this spring, which hits that one like a domino effect, you can see that this is parallel to each other. So when they use the word perpendicular, transverse. When they use the word parallel, that is longitudinal. Okay? Let's keep going. Now, parts of a wave. We've got transverse wave and we have longitudinal waves. And well, you're going to do them like go. Like put it on the. Well, yeah, but I didn't. Like.
I didn't play some computers.
Oh man, you ought to see these big ones. They're like on big stairs. They're so fun. Got it. Okay. So that way, the students have on the stay on the ground. On the ground. Okay. So don't move. Oh, we can see it good on the video, kind of. So real quick, let's talk about a little bit of waves or vocab. So whether you look on the ground or whether you look at the screen, if you have one wave, that is called a pulse. One wave. If you've got multiple waves, that's a wave train. And that would be because Barry's holding that end over there. What do we call that? A standing wave. Kind of like a guitar or like a piece of rope that's attached to one end, right? What would we see? What did we see here? Nodes and antinodes, right? Like in your notes, okay? Now, don't let go. Now, also though, with we have transverse waves, which oops, hold on. Maybe if I move back a little. So there we go. We have crest, we have trough, and we have wavelengths. Now, longitudinal waves, don't let go. They have those words, what's it called? Compression and rarefaction. And that's so weird, a rarefaction. Like, what the heck is a rarefaction? A rarefaction is where it's going to be apart. So when you look at the longitudinal wave up there, you see the compression and the refraction. Now, when we're measuring a wavelength, it would be refraction to refraction or compression to compression. I think that's about it. Yeah, I think so. So I just wanted us to see some of those vocab words. You know what? I need like an actual, I need like a legit IT person that would just sit here and just record. Like a person just to, that's their job. In classes, just sit here and record for me. There we go. Okay. And so we looked at transverse wave, crest and trough. Equilibrium would be when it wasn't moving at all. Longitudinal waves have the compression where it's smushed together and refraction that it's far apart. What I want us to know is this is easy. On the semester exam, if they ask you, measure the wavelength, I would go from top to top and use my ruler, or I would go from middle to middle and use my ruler. But where in the heck do you measure on a longitudinal wave is the question. Because a wavelength would be crest to crest, on a longitudinal wave, it would be compression to compression or refraction to refraction. So I'm going to skip real quick. I like this picture. If I have to measure a longitudinal wavelength, I'm going to measure from the middle of the compression to the middle of the compression, or I'm going to measure from the middle of the refraction to the middle of the refraction with my ruler. And that would be a wavelength, 3.7. 3.7. Look at that, 3.7. Doesn't matter if you're doing compression to compression or refraction to refraction. So what I'm trying to say is when I measure wavelength, it's from the middle to the middle or the middle to the middle. And I thought the other picture was better. We know how to do frequency. We've done it even on the previous unit. We can do the math. I'm skipping that. Oh, but let's talk about constructive, destructive interference. So, you go, oh, I'm not, oh, should we, yeah. Oh, how do we, oh, okay, gotcha. Okay, so for constructive, destructive interference, okay, you're going that way, and I'm going that way. Yeah, me too. Ready? We're both going that way. Ready, set, go. Scoot your thing over there. Ready, set, go. Scoot over a little more. A little bit more pep in your step, okay? Like try. Okay, ready, set, go. Ready, set, go.
Am I supposed to like whip it back? Like?
Yeah, just one good.
Oh, okay.
Okay, ready, set, go. Oh, that was good. Did y'all see that? Ready, set, whoa. Ready, set, go. Oh, that was a good one. So what are we doing?
Hitting it back.
No. Ready, set, go. What are we doing? And what's happening whenever our two waves meet?
They bounce back.
They bounce back, but what happens when they meet at that one spot? Ready, set, go. It gets bigger, constructive interference. So now, you're going to go this way, and I'm going to go the opposite way. Ready, set, go. One more time, ready, set, go. Oh, I messed up. Ready, set, go. Go. It's kind of about where Vaughn is at. Ready, set, go. Ready, set, go. It gets to the point where it's dies off, and then his wave and my wave. So my wave is traveling over there, and his wave is traveling to me. So we were trying to form, what was it? Destructive interference. One more time. Let's see. Let's see if we can do it. Ready, set, go. Can y'all see it? Ready, set, go. I'm gonna blend out what I'm doing. We're done. I have a better example. I've got a better one, I think. I know, not easy, is it? It's not. It's It's all like cricket. I think they could be able to.
I don't know how to.
I don't either.
There
Y'all
you go.
agree
They
that's
can
good
just
enough?
tilt their head.
That's what I agree. I agree with that. They should just move your head. All right, so here we go. How about this? We've got constructive and destructive interference. So when an obstacle or something's in the way, or when those two waves are going to combine, they form constructive, destructive interference. And so the spots where they're really dark right there, constructive interference. The spots where it's really light right there, destructive interference. Constructive, destructive. Constructive, destructive. Kind of like in your picture right here. Let me give you a better example. Constructive, look, I'll tilt that. That way he'll be straight when they video it. All right, so Vaughn, serious question though. Microwave, do you microwave often? I do too. All the time. But when you open up the microwave, what's inside of there? What, and what's the plate do? Turn, spins. Like, I mean, DJ spinning or what? Like, what's it for?
To make your food get even.
To distribute.
Okay.
You don't need a lot of food.
Okay. What if the plate wasn't there?
You
It-
don't need to sit there.
Would it work though? I mean, would my food heat up?
Yeah.
How?
The light.
Say it again?
The light.
Nope, the light has nothing to do with it. There's microwaves, and so my food would still heat up. I agree, my food's still going to heat up. But it's not going to be quote unquote, what was that word you used, Trevor? It's not going to be
Distribute.
distributed evenly. He was using big words. It's not going to be distributed evenly. And so they use that plate. And so I wish we had a full year of physics, because this semester we kind of talk about why is this here, or why is that there? Why is that plate there? I agree, because it's going to, quote unquote, make my food evenly. Now, does it distribute the heat throughout it evenly? No, that's not why it's there. It's there because if I didn't have the plate, what's going to happen to my food when it heats up? It has different what on it? Like if I had a plate of food or a to-go box, different sections, and the different sections are what? They're different foods, and got my different foods in my different section of my big to-go box. And it doesn't rotate because the rotator plate is missing. How does my food heat up?
Only one side is going to heat up.
Some of it's only hot, and then the other part is really cold. And it's like, what do you do then? If your plate's not in there, it's not working. If I had to figure a way out, what would I do? Take my food out and do what? Rotate my own food. So we all agree on that. Okay, so now let's talk about that. Microwaves are invisible waves inside of your microwave oven. And so when you click the little start button, these invisible waves are coming in, literally hitting your food. But when they hit your food, if the waves inside that little square box are on the same side of the equilibrium, they form constructive interference, and that's where your food is super hot at. Now if you got a frozen TV dinner and you have those spots that are cold still and they didn't heat up evenly, that's because I had destructive interference occurring inside my microwave. That's the reason why you have the plate to rotate it. It's not because it's going to distribute the heat evenly. It's because in locations inside of your microwave, you have constructive, destructive interference. And so for your food to heat up evenly, we have to rotate the food. That's what's in there. So that is constructive, destructive interference. We saw standing in a pulse. We know that reflection is easy, right? You see your image in the mirror. But if it was to hit at 52 degrees, it's going to shoot out at 52 degrees. That's what's going to be tested. Whatever angle it goes in is the angle is going to come out. But here's the but. It's a smooth, hard surface. Now, for quiz test, reflection, keyword is bending. I can cause a wave to bend. Let's say we have the sun and the light is shining through. It's outside. The sunlight can travel faster in air molecules than it can in water molecules because the water is more dense than air. And so when the sunlight travels through the air, it goes at whatever speed, 3 times 10 to the 8th power. When it goes through water molecules, it slows down, and when it slows its speed down, it bends, or what we call refracts. Okay? So the key thing here, light is bending because it travels through 2 different mediums. Bends because it's traveling through 2 different mediums. But diffraction is when a wave is going to change its direction, don't use the word bend, around an obstacle and is going to continue to travel. And here is our bending. And when it bends at this location, you can see it right here. You've got constructive interference. So right there, when those things are touching each other like that, constructive interference. When it's not, those spots are destructive interference. Next spot, next thingy, because like I said, I know we're not going to get through all of it, but we are going to get through most of it. Get your cup and your tuning forks. So tuning forks. All right. So when you're using the tuning fork, I have no problem with you hitting it as much time as you want to, but don't hit it on the table, please. Hit it on the bottom of your shoe. Oh, it's because I took it. So you can hit it at the bottom of your shoe. Don't hit it on the table, is what I'm asking. Like, I'm going to hit it on this, whatever. Hit it on your, I don't know, hit it on your knee if you need it to. But give it a good hit this way. So you're going to hit this side of it. So you're going to use it, you're going to hit this side onto something, and it's going to start to vibrate. Right? Now, I think tuning forks are so cool. So let me grab these two. So hit your tuning fork so you can practice. Can't you hear it? Put it by your ear. You hear that little vibration? Right? The other one, make sure it works. Hold it at the bottom, because when you hold it at the little prongs up here, you stop and you slow the vibration. So hold it down here at the bottom. Now, let me show you something, because I don't know, I think this is such a cool thing. I'm going to come around, I'm going to touch you with my tuning fork, okay? But you're going to cover your ears as hard as you can and try not to hear me, like this. I'm going to touch your elbow. I need to see your elbow. It's not going to hurt, I promise you, unless you have in mind. But nobody, I don't see nobody right now that it would hurt you. So watch, as tight as you can. Yeah? Oh, get the nose ring. Let's. Do you have braces? Do you have braces?
Wait, what?
Do you have braces?
No.
Somebody's got to have braces.
Robert has braces.
Do you? Let's do your teeth.
I do not.
Let's do your teeth.
I do not.
I've never had braces, but I don't know. Can we? Oh, I wonder if it hurts. Tickles. Let me see your elbow. You got a hoodie on, but it's gonna work. No. You hear it?
Yeah, it sounds like a chipmunk.
You hear it?
I was up there looking at some board.
Why does it sound different when we hit it like this instead of like this?
Because this needs to vibrate this way, not vibrate this way. They have to vibrate this way, that's why. So, okay, when I went around and I touched your elbow, you were able to hear it, and you can also like feel it going through your body, right? So why can you hear it even though you had your ears closed? Because sound has to travel through a medium, and your body became the medium for it to travel through. Now, if you, and I've done this before, I think this is hilarious though, but that's just me though. But you know, this is your first x-ray machine they never had, because they didn't always have x-ray machines. So a long time ago, doctors, if you thought you broke something, and in my house we got the 3-day rule. If you think you broke something, you just let me know day 1. Day 2, go take some, I don't know, Tylenol or something, right, under the counter that we have. But day 3, if you still think it's broken, then you let me know and I'll take you to the doctor. 3-day rule is what it's called in my house. Doctors can't do nothing day 1. I mean, what, just go spend money for my copay, and they're going to say, oh, it's still swelling, got to come back when the swelling goes down, and then we can cast it. So here's how I tell at my house if you've got a broken body part. Long time ago, this used to be the x-ray machine. So what the doctor would do was hit it, and if you think you broke your wrist or your arm, they would get this in, like I did to your elbow, and they would touch it. And when they touched it, it would be unbearable pain. Like you will start screaming because your bones that are fractured or broken, they will start rubbing against each other, and it's real painful. Old school x-ray machine. You can tell if it's broken. It didn't hurt you when it went through, but if your bones were broken, it would hurt. Did you break it?
No, I was just.
Oh, did you? Okay. I don't know. I mean, I don't know. That was not enough to look at the other one.
Yeah, this is a C. They're both C's.
Okay.
Does somebody want that?
I have a C.
That would be to be.
No.
I'll just say it on the bottom.
Yeah, I have a D. I have a C. I don't. She has an F. You want to trade an F with her?
Is F and C are a bit apart, which means they're consonants, so when they're together, they.
Well, and now I gave you the same ones. If you look at both of them, they should be the same, and they're the same on purpose, though. So we'll talk about that in just a moment. For what? No, they ring together, absolutely, when they're the same ones. Certain frequencies ring at different locations and together. So let's take a look at this one. So first thing is, this is old school x-ray machine. Can I cover up my ear and I can still hear it? I can also feel it as it goes through because my body became the medium for it to transfer through. But it says here, go ahead and get some salt and put some salt on your, you see your hand? On your, get some salt and put it on your cup, on your plastic part of your cup. Just, I would make like a little pile in the middle and then put a few sprinkles one more.
Is it gonna be like when you put something like on a speaker and it starts bouncing around?
But we're not going to touch it though. But don't touch it. So I would try to put it like on a little pile, make a little mountain, and then put a few of the sprinkles over to the side by themselves, like that. So make a little mountain, but then put some over to the side by itself. Anybody need some more? Need some more? Okay, we got plenty if y'all need more. I bought a whole new one yesterday. So I'm going to go ahead and I'm going to and then I'm just going to put I'm going to just put a little bit around, but I'm going to make a little mountain right there in the middle. So it says here, tap your tuning fork on a hard surface, bottom of your shoe, and notice the hum. You're going to hear it in your ear. But hold the tuning fork close to the salt, but do not touch it. Now, not by the big part. Whoa. I ain't gonna lie, that scared me. Here we go. Over here on the edge. Remember how I said get a few of those thingies by themselves? Go ahead and go near the ones that are by themselves, not the big pile of it. If you need to, spread them out. They start to do what? They're moving, and I'm not even touching it. Don't touch it. We're going to touch it in a minute, not yet. Look, you can see my little thingies. They're moving. You can probably see yours moving. If you need to, hit it a little harder. If you really need to hit it on the table, go ahead. But put it near it. It's not here. How about try this one? It's not working. Hit it on here. Here you go. Look at you. Too many. Hit it on the table then. Hit it on the table. So the question says, what do you observe when you get near it? The salt starts to move, right? So answer your question right there. What happens? What does the salt start doing? It starts to move. Now, my question though is, why is the salt moving? Even though I'm not touching it. Remember last unit, I ate Tostios, ate them again this morning, and I came over here and I pushed the chair. I physically touched the chair and I caused the chair to move. You're not physically touching the salt, but it's moving. Why is the salt moving? Nope.
The power of the
Air is the medium. Okay, so keep going. Barry, give it to me.
vibrations.
Okay, but what are those vibrations? What's going on?
Wave stuff.
Okay, which is transferring what? Energy. Because all waves have one job, it's transfer energy. And so when I hit it, and I come over here and I make a move without touching, the air molecules becomes the medium, and the energy transfer is coming from my tuning fork over to the salt and causing it to move. Now, let's go ahead, hit it really nice and good if you need to on your table. Touch it. Touch it. Whoa, touch it all the way. How does the salt move now? In your eyes. It starts to like splatter everywhere. My question now is, why is it splattering everywhere?
Because it's
There's a lot of
not
energy.
the waves.
Not that there's a lot of energy. Okay, how about this? What if I hit it really softly? It still made it good. Not because of the amount of energy, because if I hit it harder, boom, I got more energy. If I hit it soft, I still got, look at that, was still a lot of energy. Not the energy. Why is it splattering bigger? Because sound travels fastest through solids versus a liquid or gas. And so when I didn't touch it, what was my sound traveling through? Air molecules, which is a gas. But the moment that I touched it, it was solid to solid. It transferred faster, and those salt was bouncing everywhere. So answer your question. I got salt everywhere. And then just knock your salt off to the ground. Answer your question in your notes. Knock your salt off to the ground. It's okay. I promise you, they vacuum and sweep. Yeah. So answer your question. Energy sound is being transferred from the tuning fork to the salt. But don't forget, it went very little when it was going through the air molecules. But the moment I touched it, it boom, bounced a lot more because it was solid and solid. And sound can travel faster through a solid than a gas. Okay? I know we're running low on time, and I apologize. And like I said, we're going to get through most of it today. And whatever we don't, we're going to video, because I have some students who are just not here. And it's not fair to them, so we're going to video it anyways. Next page. We're going here. Now, this is, quiz test. Humans can hear between 20 and 20,000 hertz. Less than 20 hertz is called infrasonic. Greater than 20,000 hertz is called ultrasonic. Now, let's go ahead and take an example. Let's look at this part over here.
As we grow older, we often lose the extreme ends of our hearing spectrum. So, how many of the following sounds can you hear?
It's a hearing test.
How old are your ears?
Like one of those. I hear it.
Okay, if you can hear 8,000 hertz, you're both alive and not hearing impaired.
Good.
But let's keep raising the frequency.
Heard it. Now I'm going to pause it real quick, because I get some students that say, oh, I hear that. No, you didn't, because they're going to go click, click, you're going to hear like that. That's because they're turning the frequency on. That's not what you're listening for. You're not listening for the no, you're listening for the actual beep. Okay, get ready. Nope. I can't hear it.
You can't hear
No.
that?
Look, I don't hear it.
You can't hear
No.
that?
I don't hear it. No. I hear it a little bit.
I hear that one. I hear that one.
How high could you hear? If you could hear all of those frequencies, you're probably under 20 years old. But that won't last forever. Unlike other organs
I
such
can't
as the
hear 'em.
liver or
Like, I
skin,
literally
the
can't hear
inner
'em.
ear does not have the capacity to regenerate. In your ear, there are thousands of tiny nerve cells called hair cells. These are responsible for picking up different frequencies and sending the signal to the brain where it's processed. But as you age, the continual exposure to noise and loud sounds can break, bend, and destroy these cells. So why do the high frequencies go first? It turns out that the hairs tuned to high pitches are the first to encounter sound waves. As a result, they experience more stress and tend to degenerate earlier, which is why the older you are, the harder it is to hear high pitches.
Yeah, I couldn't hear those. Those are. Woo. So greater than 20,000 hertz, again, we can't hear it. That's like dog whistles or bats. And we also use ultrasonic for ultrasounds. What happens here is that they send out waves, and when the waves hit a solid material like an organ or something or a baby, it sends the waves back and is able to make an image. So that's what ultrasound is. You remember that question from your homework? What was the speed of sound through in outer space?
Yeah.
Zero.
Yeah.
Zero, because sound can't travel in outer space because there's no medium. Let's keep going. So, Doppler effect. On the Doppler effect, here's what I need us to know for sure. It's a change that occurs, but you as the person, you don't move. It moves. Let me give you an example. I'm saying I move to the side, I hear a fire truck, it's coming, it's coming, it's coming, it leaves. Meteorology. They said today, I don't know if I watch news, Channel 11 News, I don't know. It's easy, it's like 1-1, hit enter. That's why I can't watch Channel 11 News. It said this morning we're getting a cold front this afternoon, right? I think they said what, like 89 degrees, 86 degrees? That's a cold front for us. What's moving? Am I moving? No, the weather's moving. Let me just give another example. Astronomy. I live here on Earth. I'm not planning to move to any other planet. What is moving? The galaxy is expanding, not me. Okay? So when it comes to this is whenever you have one object is moving, but you as the person, you're not moving. It's the Doppler effect. Let's keep going. Sound intensity. Decibels is the correct SI unit for how loud something is. You can get to a point where the loudness is so loud, look at this amplitude, it's so big that it physically hurts your ears. You can hurt somebody's ears. Now at the bottom of the last part, let's go to resonance. So resonance definition is the ability when one object vibrates, it transfers energy to another object. That's why you have two tuning forks with the same numbers on it. So I've got a C of 256 and 256C. What you should be able to do, and I'm not saying it's perfect, but you should be able to hit one of them, put it near the other one, don't touch, move it out of the way, and hear it vibrate. Hit it, don't touch, get them close. Move that first one way out of the way and hit and hear the second one. I hear it. Now it's not super loud, but I hear it. What's happening here is that this one is vibrating because I hit it. It's vibrating. It transfers energy to this one because they are the, look at this, same frequency. It is able to cause this one to start vibrating also, and now this one's also vibrating because they're the same frequency, okay? And on the last part of it, do you see the one that says singing wine glasses? Put an X on that. I'm going to video or show on Blackboard the opera singer. Can an opera singer really break glass? So it's a quick 5-minute video clip that I'll show for us so that way we can see that one. But it looks like I'm out of time because I have a thingy on black or whatever, blah, blah, blah. So,
You got stamped?
yes, homework. Now I'm gonna put all the answers though on Blackboard.